this lesson is the derivative of logarithmic and exponential functions. We know that y equals e to the u means that the derivative y prime is e to the u du, where u is a function in terms of x. We're using the chain rule. Now we play off of this to find the derivative of logarithmic functions. So we need to know this in order to find the derivative of logarithmic functions and to find the derivative of exponential functions for bases other than e. Here are the tools we'll need. We'll need the chain rule. We'll need implicit differentiation. And we'll need, from an earlier course, the definition of logarithm. Here's the definition of log. The log of a to the base b equals c means that the base b to the c power equals a. We need this definition, so we have to use it several times even in this lesson. Now notice that the base is positive and a must be positive. Okay. Now c, which is the log, happens to be an exponent, and because it's an exponent, it shares the properties of exponents that you found in earlier algebra classes. That is, when you have the same base and you multiply, you add exponents. When you divide, you subtract exponents, and so on. And we're going to be using that during this lesson, so we bring that up. Let's look at some examples to make sure you understand what that definition we just observed means. Log of 8 to the base 2 is 3. Why? Because 2 cubed is 8. The log of 625 to base 5 is 4, because 5 to the 4th is 625. And the log of 1/9 to the base 3 is -2, because 3 to the -2 means 1 over 3 squared, which is 1/9. So maybe those will help you recall better the definition of the log. If the base is 10, it's a special kind of logarithm. It's called common logarithm. And we don't include the base when you're doing a common logarithm. In other words, if it says log of m, it's assumed that the base is 10. We're not going to write log 10 if the base is 10. We're simply going to write the log. The absence of a base value means the base is 10. That's important. Let's make some notes here. Therefore, when we say log of 1 million, we mean base 10. And we're asking, what do you raise 10? What exponent do you raise 10 to in order to get a million? And the answer is 6. Okay, so the log of 1 million is 6. The log of 1 to any base is 0. Remember, the base is a positive number because any positive number to this positive real number to the 0 power is 1. So that's important to know. Also, what we've done here is we have graphed for you y equals b to the x, where b is some positive base, and the log of b, base b of x, where b is that same base. And we notice these are the graphs we get. This is y equals b to the x, and this is y equals log base b of x. Now, if you recall from earlier courses, these are inverses of each other, because this is the line, this dotted line is y equals x. And if you fold this over along the dotted line, they will be superimposed on each other. Or another way of saying, if this is a mirror, this is the reflection of this graph behind the mirror images of each other. Now, the reason we mentioned that, because we need this property in calculus. That is, f inverse of f of x equals x, and f of f inverse of x is x. That's from, again, from earlier courses. What that means is the log y equals b, log of bx is x, and y equals the log base b of b to the x is x. And we will be recalling this later in this course, and when we do, we'll remind you of that fact. Now, as we said earlier, a log is an exponent, and you had laws of exponents in beginning algebra. And since this is an exponent, we can use those laws and apply them to the logarithm. In other words, we call this the properties of logs, where b is any base. Now, we have not written the base here, okay, to keep it simple, because it's true for any base. So we'll just do it for common logarithm here, but it's true for any base. Log of a times b is the log of a plus the log of b, because when you multiply and the base is the same, then you add exponents, remember. Logarithm is an exponent. So the log of a times b is the log of a plus the log of b. Likewise, the log of a divided by b is log of a minus log of b, because from algebra, when you divide, you subtract exponents. The log of a to the m power is m times the log of a, because when you raise an exponent to an exponent, you multiply exponents. And in the special case, the log of nth root of a, remember nth root means 1 over n power, is 1 over n log of a. We are going to need these properties in this very lesson that we're in right now, and we'll recall these later when we do use them. Okay. Now, in calculus, e is the base we use most often. Now, we said just a few minutes ago that the log of x means base 10. If you see no number written down, the common logarithm. Well, since we're going to be using e as our base, but find it awkward to keep writing log base e of x, we need some additional notation, okay? Because if we will be putting this down all the time, we don't want to. But yet, if we don't put it, it means base 10, and so there's going to be a lot of confusion. So what we're going to do, if the base is e, we're going to write ln. ln means natural log. N stands for natural log. It's called the natural log. That when you see ln of x, that means the base of e. So if you see log of x, it means base 10. ln of x means base e. If it's any other base, we would have to write log and put the little number as the base into the problem or function. Since this is calculus and we're always interested in derivatives, how do you find the derivative of the log function, the natural log function? Okay, ln of u. So that's our task, and let's see if we can come up with a formula. So y is equal to ln of u. Now, what does that mean? Well, think about the definition. If the log is y, that means the base, which is e, to the y power is u. So y equals natural log of u means e to the y power is u. That's definition of logs. Now what we're going to do is we're going to take the derivative implicitly. Now we know how to find the derivative of e to the y. It's e to the y, and it's a y term, put a y prime with it, and the derivative of u is equal to u prime or du. That's implicit differentiation. Now our goal is to find y prime, so let's solve for y prime, which means divide each side of the equation by e to the y, which we do. But we know that e to the y is u. U is e to the y. E to the y is u. So we can substitute in the place of e to the y, u. And so y prime is du over u, or u prime over u, depending on how you prefer to look at it. So that is our formula for the derivative of the natural log of u. And we can put that in our toolbox. Let's look at some examples. Example 1, y is equal to ln of 3x squared plus 2. Find the derivative y prime. Well, the derivative is du or u prime. Now this is u, 3x squared plus 2. So the derivative of this is 6x over u itself, and we're done. It's pretty neat, pretty simple, is it not? Let's take another example. The natural log of sine of x. Well, u is the sine of x. Du, or the derivative of sine of x, is cosine of x over itself, and so there's your answer. Or, since the cosine of x over sine of x is the cotangent of x, we could leave the answer that way. Each answer is good. Now, one of the things we try to do in this series of lectures is when we have a new tool, we try to review as many of our old tools as we can. Now, when I say review, I mean we want to review the product rule, we want to review the quotient rule, we want to review the second derivative, we want to review the chain rule, we want to review the equation of a tangent line, and so on. So that's what we're going to be doing in some of the upcoming examples now. Y equals x cubed ln of x. Find y prime. This is a product, so we're going to use a product rule, which is going to be the first, x cubed, times the derivative ln of x. Well, the derivative of x is 1 over itself, plus the second, ln of x times the derivative of x cubed is 3x squared. This x cancels into one of these, leaving us x squared. And let's put the 3x squared out front. And there's our answer. Or we can factor an x squared, and that's a good answer. So that's a review of the product rule at the same time using our new tool. Example 4, y equals ln of x divided by x squared. This is a quotient, so let's use our quotient rule. Denominator times derivative of numerator. Well, derivative of ln of x is derivative of x over itself. It's 1 over x minus the second, minus the numerator, which is ln of x times the derivative of the denominator, which is 2x, all over the denominator squared, which is x squared squared. The x is canceled, leaving us with this. Get the 2x out front, square this, we have that. Of course, we can factor an x. That's a viable answer. And look, you can cancel this x into this x to the fourth. I think if you get this far, you would expect to do that. And that's another form of the answer. So that takes care of example 4. And we have reviewed the quotient rule, and also we're instilling the definition of the ln of x into your thinking. Now, this next example is ln of x plus y equals x plus ln of y. We're going to have to use the implicit derivative here. The derivative of ln of x is the derivative of x, which is 1 over itself. The derivative of y is 1. Put a y prime with it. The derivative of x is 1. And the derivative of ln of y is the derivative of y, which is 1 over itself. And put a y prime with it. Now we want to get one y primes on one side, so we're going to bring this one over to the left, and that's going to give us 1 minus we'll give y prime minus 1 over y prime when we do. And then we're going to leave this 1 here and bring this term over, and this is going to give us 1 minus 1 over x, okay? So we're bringing this term over to the right and this term over to the left. That's all we've done in this step here. Now we'll factor out a y prime out of of this. And when we do, we are going to get y prime is equal to y prime times 1 minus 1 over y is equal to 1 minus 1 over x. And now we'll divide everything by 1 minus 1 over y, and that gives us this. Okay, a little tongue-tied problem here. We're not really quite through with this problem, however. It's a great review of implicit, and that is an answer here, but there is a better answer. See, this is called a complex fraction. Just remember, a complex fraction is a fraction whose numerator and or denominator has a fraction in it. And this, both that numerator and that denominator have a fraction. And here's what you do. Call it a trick, if you will, but this is the procedure. Multiply the numerator and denominator by the least common denominator. Since our denominators are x and y, then the least common denominator is x times y. So let's multiply the numerator by x times y. When we do, x times y times 1 is x times y, and xy times 1 over x, the x is canceled, leaving us with just y. Now multiply the denominator by x times y. When you multiply 1 times x, y, you get xy, and when you multiply 1 over y times y, you get negative x. And so this is somewhat more acceptable answer. So work towards getting this. But please make sure you understand implicit differentiation. The only thing, this is just a simple implicit differentiation problem going through the menu. And the only thing new is we now have the log function to deal with. So this is a great review problem of the implicit derivative. Let's review writing the equation of a tangent line. Given y equals ln of 2 minus x, find the equation of the line tangent the graph at 1, 0. And this answer will be fairly simple, so we'll request that you leave it in the form y equals mx plus b. Note that 1, 0 is a point on this line. When x is 1, then you have ln of 1, which is 0. We said earlier, ln of 1 is always 0. Log of 1 to any base is 0. So this point is on the graph of this equation. So we have our point, we need slope, so we need derivative. So the derivative of this is the derivative of this quantity, which is -1. We'll put the negative sign out front. 1 over itself. Okay, we want the slope at x equals 1, so put 1 in for x, and that gives you 1 over 2 minus 1, which is 1 over 1 with a negative sign in front of it is -1. And so now we use our point slope formula. We plug in for y1, we put in 0, and for x1, we put in 1, and for our slope, we put in -1. And there's our answer. And we can check that since we can easily graph this and easily graph this. And they should be tangent at the point 1, 0. If they're not, that means you have an error and need to re-examine the problem. Now, example 7, we want to find the second derivative. Well, to find the second derivative, you need the first derivative. So let's find y prime. That's going to be the derivative of this, which is 2x over itself. That's the first derivative. Now, the second derivative, we've got to use the quotient rule, which is denominator times the derivative of the numerator, which is 2, minus the numerator times the derivative of the denominator, which is 2x, and all over the denominator squared. Now let's put this 2 out front over here if we can, and let's multiply this -2x times this 2x gives us -4x squared. And then if we distribute this, we get 2x squared minus 4x squared is -2x squared plus 2 all over the denominator squared. That's a good answer. Or you can factor out a 2, and when you do, you're left with 1 minus x squared over the denominator squared. And so we have 2 viable answers there, 2 forms of it, each of which are probably acceptable. Let's go to problem 8 now. Problem 8, y is ln of x plus 3 cubed times x squared plus 1 divided by x minus 5 to the 4th power, and we want the derivative, which means up to now that we've got to take the derivative of this thing and then put that answer all over itself. Now, this is going to be quite a job. Denominator times this, and that's a product. This is going to take quite a bit of time. But no, it's not. Remember our properties we had a few frames ago. This is a product, is it not? And when you have a product, you add logs. This is to a power. When you have a log of a power, you put the exponent in front of the log. And when you have a denominator, quotient, you subtract logs. So let's see if we can put this all together. We'll take the log of this. Just concentrate on this term right here. The log of this, and this is to the 3rd power, so it's 3 times the log of this. Since this is multiplied, that's going to be plus the log of this. And since this is divided, it's going to be minus the log of this, but this is to the 4th power, so we put the 4 in front. And now, let's take the derivative. The derivative of this is 1 over itself. The derivative of this is 2x over itself. And the derivative of this is 1 over itself. And we have a 3 in front and a 4 in front. So let's multiply this. 3 times 1 is 3. 2x over x squared plus 1. And the negative 4 over this. And we're done. Wow. You certainly want to know the properties of logs. Otherwise, this problem is extremely time-consuming and also so meticulous that you've got to be so careful to see, not to make a mistake. You want to know the properties. If for no other reason, this is one of the reasons, but not the only reason. But I'll warn you, most people, when they look at this problem, they walk away from it. And rightly so, because they think they've got to take the derivative of the quantity and then put it all over itself, and you've got a lot of work on your hands. So please, when you come to a problem like this, think back to this and remember this. And in essence, it's a problem you can do in your head if you're really good at it. In other words, you look at this and say that 3, take the derivative of that times 3, and you get it. And you say that's plus the derivative of this, 2x over the self. Then you take the derivative of this with a 4 in front, subtract. You can do it in your head. You can look at this and do it in your head. Work at that. Work at being able to do that. Okay. Now, we said earlier that this is about finding the derivative of logs and exponential functions. And we already know how to find the derivative of e to the u, but what about other bases? Like the common log, or common base, 10. How do you take the derivative of 10 to the x? It's not 10 to the x. Okay. How do you take the derivative of 2 to the x? It's not 2 to the x. Now, something we said earlier should let you know that the derivative of 10 to the x is not 10 to the x, and derivative of 2 to the x is not 2 to the x, because we said earlier, e to the x is the only function whose derivative is itself. So if the derivative of 10 to the x were 10 to the x, then that would have been a misstatement earlier, and it's not. Now, we'll tell you that the derivative of 2 to the x is close to 2 to the x, it's just not 2 to the x. And the derivative of 10 to the x is close to 10 to the x, but not 10 to the x. So let's see if we can derive a formula for finding, given y equals b to the u, where b is a positive integer, find y prime. So let's start. Y equals b to the u. First thing I'm going to do is I'm going to take the log of each side of the equation. That's what I've done. Natural log of y, natural log of b to the u. The reason I'm using natural log and not common log is because I know how to operate NAF, because of the formula we just got, the derivative formula, how to work with natural logs. I don't know how to work with common logs from a calculus point of view. So I'm going to take the natural log of each side. Talking a lot here, but that's important. Now, that's legal as long as you do it to both sides. Now, why am I doing this? Well, notice that property, the log of something to a power, let's use that property. In other words, I'm going to leave this term alone. Ln of b to the, ln of y, I'm going to leave that alone. And I'm going to write ln of b to the u power is u ln of b. That's that third property of logs. Now what am I going to do? I'm going to take the derivative implicitly. The derivative of ln of y is the derivative of y, which is 1, over itself, y, put a y prime with it. And the derivative of this thing, well, remember, ln of b is a number. So all I'm really doing is taking the derivative of u. So that's u prime, or du if you wish. Okay. Now what I'm going to do is I'm going to take this. Remember, what do I want? Y prime. So I want y prime, so I'm going to multiply both sides of the equation by y. Now, when I multiply the left-hand side of the equation by y, the y in the denominator vanishes, and I have a y here. Okay? Now, I'm almost finished. Remember now, what is y anyway? Y is b to the u. So I'm going to substitute in the place of this y, b to the u. So that's what I've done. The only difference between this line, this term, and this is I now have replaced the y with b to the u. And now let's kind of rearrange this. This is b to the y, ln of b, u prime, or y prime is b to u, ln of b du. Either way, that's our formula. In other words, basically it says, if you have base, some other base, say 10 to the x, it's going to be 10 to the x, ln of 10, not log of 10, ln of 10 times the derivative of the exponent, which in that case would be x, which is just 1. So if you have something to another base, it's what you hoped it would be, okay, times ln of the base times the derivative of the term if it's other than x. Let's quit talking here and let's look at an example. I think that's the best way to learn this. So let's take the derivative of 2 to the x. Okay, we would hope it'd be 2 to the x, but it's not. But the formula says ln of the base, well, ln of the base 2, that's ln of 2, and then the derivative of x is just 1, so we are done with that problem. Got it? Let's look at this. This is a product rule problem, okay? So let's use the product rule. Derivative of this will be first times the derivative of this. Now, what is this? 5 to the x, ln of 5. Of course, the derivative of x is just 1, plus a second, 5 to the x times the derivative of x to the 5th, which is 5x to the 4th. And now let's clean it up a little bit by getting numbers in front and everything. So here is a viable answer here, okay? Here's a viable answer here. And we can also, since we have an x to the 4th and an x to the 5th, we can factor an x to the 4th. And since we have a 5x here, 5 to the x here, and 5 to the x here, we can factor out. So this is the factored form of this answer. But both answers are good answers, okay? So we're reviewing the product rule, and we're using what are we doing new? Using our new formula, a new tool, and that is the derivative of 5 to the x is 5 to the x natural log of 5. Okay. Now, example 11. 7x cubed, 7 to raised to the x cubed power. Well, the derivative is going to be 7 raised to the x cubed power times the derivative of the exponent, which is 3x squared. See, the other problems, the exponent was x, so the derivative was 1, times ln of the base. Okay, you can leave it like this, or we can leave it like this. or we can go ahead and multiply the whole thing out and leave it like this. So this is probably the safest way to leave the answer, leaving it like this. We're not going to explain to you how we got this answer. We'll leave that for you to think about that particular problem there, where we got this 343. Well, we'll go ahead and tell you. 3 ln of 7 is, using the property, that would be the same as ln of 7 cubed, and when you cube 7, this is what you get. So okay, this is but if you'll not let us confuse you too much here, see if you can get it to this point right here. So you really do want to know how to take derivative of other bases, especially in the case of some of the biological sciences where base 2 is often used when you're having working with cell division and things of this nature. So we do need to know how to handle other bases. Now, consider the following. This is less important. Seldom do you have other bases for logs, but since we're so close, we're going to go ahead. And how do you find the log of some other base than base e? Okay. In other words, we know how to find the derivative ln of u, but what if you have some other base, i.e. the common log, base 10? What are you going to do? So let's see if we can come up with an answer. Start here with y equals log base u of e. This means, by definition of log, that b to the y power is u, okay? That's just from the definition of the log. This is our base. This is our exponent. So b to the y power is u. Now, let's take the log of each side. The log of natural log of b to the y is this, and the log, natural log of u is this. We take the log of each side. Now we're going to use our property, which says that the natural log of b to the y power is y times the natural log of b. We'll just leave this alone. And now we're going to take the derivative implicitly. This, remember, is a constant, so the derivative of y is 1, put a y prime with it. So that's the derivative of this. And the derivative of ln of u is the derivative of u over itself, u prime over u, or du over u. Okay, now we want, what do we want? We want y prime. So let's divide each side of the equation by ln of b. So that's what we've done here. Okay, and so that's our answer, or we can write it like this: du over u, 1 over ln of b. So here's the formula for some other base. It's du over u. That's what you would hope. That's what it is with ln. Du over u, or u prime over u. But if the base is something other than e, you've got to multiply by 1 over ln of the base. Now notice, when we had the derivative to other bases, it was times ln of base. With the log to another base, it's 1 over ln of the base. You need to keep those straight. Let's work a problem. Now, if this were ln, remember, what would the derivative be? 3x squared over x cubed plus 1. But it's not. Ln, it's log of base 2, so we've got to multiply by 1 over the natural log of the base. Okay, so if you can remember, if you can handle ln, which is 3x squared over x cubed plus 1, and if it's base e, ln, you're through, but it's not, it's base 2, so you have to add this at the last 1 over ln of 2. Let's take another one. This is a review of the product rule and some of that trig. Don't fall to pieces when you see something like this. Remember, we're trying to review as we go through this. This is a product, so you have first times the this is the problem is given. We haven't done anything yet. We're just restating the problem here. So the derivative is the first times the derivative of this. Now remember, this is 5 over itself times 1 over ln of 3, because the base is 3, plus the second ln of 5x plus 1 base 3 times the derivative of tangent is the secant squared. And guess what? You're done. You're done with the problem. Okay. Now, logarithmic differentiation is something we want to talk about. What is logarithmic differentiation? Well, it's taking the derivative using logarithms. Before, we've been taking the derivative of logarithmic functions. This we want to take what's called logarithmic differentiation. Okay. Logarithms really come into play anytime you have an equation and the exponent, or the exponent, say x, is an exponent, then you want to think logarithms. This statement right here is most important. When you have an equation and the unknown is an exponent, say x, think of logs. Think of logs. Always think of logs when that happens, and it pays dividends. And this is an example. I have y equals x to the x power, and we want to find y prime. Now remember, I know how to take x to a number, say x cubed. I know how to find the derivative of x cubed, do I not? And I know how to find the derivative of 3 to the x. 3 to the x is 3 to the x times ln of 3. Okay, I know that. But this is y equals x to the x power, and I don't know how to find this. It's not, let me tell you, it's not x times x to the x minus 1. That's what you're inclined to do. It's not, in other words, I cannot use the power rule. So here's what I'm going to do. My unknown, my exponent's unknown. I told you, when you see the exponent's an unknown, apply logs. In other words, I'm going to take the natural log of each side of the equation. That's all I'm doing here. Natural log of this, natural log of this. Now, second, the natural log of x to the x power, that's your property of logs. I'm going to put the exponent in front. Now, what am I going to do next? Well, I'm going to take the derivative. What's the derivative of ln of y? Well, the derivative of ln of y is the derivative of y, which is 1 over itself, put a y prime with it. And then over here, I'm going to take this derivative. I've got to use the product rule, which is first. That's first term. Now, the derivative of ln of x is 1 over x plus the second ln of x times the derivative of x, which is 1. Okay. Now, this is going to be, I can cancel these x's, I get just 1. And then this is just ln of x. So 1 over y prime is equal to 1 plus ln of x. That's what I'm restating here. This 1 over y prime is equal to nothing more than 1 plus ln of x. What do I want? Y prime. So let's multiply both sides of the equation by y. When I do, this y in the denominator vanishes, and I end up with a y here at the end. And now I'm one step from being through. What is y? Y is x to the x. So let's rewrite this, and in the place of y, put x to the x, and I'm done with this particular problem. Okay? So this is known as logarithmic differentiation. Let's take one more problem like that. Y equals x to the sine of 2x, and I want to find y prime, so I'll write the problem. Now, the first thing we'll do is take the log of each side, just like before. ln of y, ln of this. Now, since this is a log of something to a power, I can put the exponent in front. So I do. Notice all I've done between this step and this step is put the sine of x in front. Now, take the derivative of this, which is derivative of y, which is 1 over itself, put a y prime with it. And when I take the derivative of this, I've got to use the product rule, which is first, times the derivative of this, which is 1 over x, okay, plus the second, ln of x, times the derivative of the sine of 2x, which is cosine of 2x, and then the derivative of 2x is 2. So that's what I get, okay? Now, I'm just going to rewrite this thing. I want to put this x down here. That's about all, and I'm bringing this 2 out front, okay? And so now, I want y prime, so we multiply both sides of the equation by y. Well, what is y? Y is the, which I do here, multiply both sides of the equation by y. That puts it over here. Losing track here, so much to see. So that's all I've done from here to here is multiply both sides of the equation by y. And now I'm one step away. Since y is equal to x sine of 2x, I'm going to substitute in x sine of 2x for y. And when I do, this is my answer. Okay, so you've seen two equations, functions that required logarithmic differentiation. Now, let's look at example 16. Given y equals 2x plus 5 over 3x plus y1, we want to find y prime of 2. In other words, find the derivative and evaluate it when x is 2. We're going to do it two different ways. The first way is what you would probably do most commonly, and that is use the product rule. So we do. I mean the quotient rule, excuse me. Quotient rule. It's denominator times derivative of numerator, which is 2, minus numerator times derivative of denominator, which is 3, all over denominator squared. Okay. Now what I'm going to do, I'm not going to clean this up since I want the answer when x is 2. I'm just going to go ahead and substitute in 2 here for everywhere I have an x. So I'll put a 2 there, and I'll put a 2 there, and I'll put a 2 here, and I'm going to do the arithmetic, and we have, and our answer is negative 13 over 49. Now, let's try a second method. This is what I'm going to do. Let's say I don't know the quotient rule. I've forgotten. Here's a way out. I'm going to take the log of each side of this equation. In other words, I'm going to write this thing, take the log of y, that's ln of y, and I'm going to take the log of this, which is all I've done here. Log of this, log of this. Now, I'm going to rewrite everything except I've got a quotient, so that's the log of the numerator minus the log of the denominator, is it not? Now let's take the derivative. Derivative of ln of y is the derivative of y, which is 1 over itself, put a y prime with it, equals. Derivative of this is 2 over itself. The derivative of this is 3 over itself. And so I have y prime is equal to this times y. Okay, this times y. Now, what do I want? I want y of 2. So all I'm going to do is everywhere there is an x, I'm going to put a 2. And now what I've done here is this y happens to be this quantity right here, so we'll put in a 2 for it. In other words, this y is this thing right here, okay? This y is this 2x plus 5 over 3x plus, so I'm going to put that in. And now I'm just going to do the arithmetic, and you're going to have to trust us that I get the same answer. Negative 13 over 49. Now you might say, I prefer method 1, and I do too. But suppose you had a complicated function that you would have to take the product rule and quotient rule several times, and it gets very complex looking. This is a way out. This is an escape way to do a very complicated problem. So we don't prescribe that in this particular problem that you do that, okay? We wanted to give you a problem that was very easy to do straightforward, and it's much more complicated to do it this way. However, if it's the other way around and the function were very complicated, this would be the way to go. You probably aren't going to run into be exposed to many of these in a first year calculus course, if in any calculus course, but we mentioned that to you. Now, here are our formulas that we've done. This has been a long journey through this lesson. We have the derivative of ln of u is du over u, or u prime over u. If the base is something other than e, then it's b to the u, ln of b times u prime or du. And if the log is some base other than e, then it's going to be du over u times 1 over ln of the base. Basically, those are the things that you want to make sure you're taking from this lesson. And these are the things you want to add to your expanding, ever expanding, we might say, toolbox. One additional observation. Earlier, we proved the power rule for n, a non-negative integer. We have since proved it to be true when n is a negative integer. You would need to see the product quotient rule lecture for that. And also true when you have a rational exponent, fractional exponent. And we say we did that, but you would have to go check that out under the implicit differentiation lecture. Now we want to see if we can do it for any real number, including irrational numbers. In other words, what if you have x to the pi? And we already realized that we've been saying all along that if you take the derivative of x to the pi, that's pi times x to the pi minus 1. But let's see now why it is legal to do that. We've been doing it all along, promising you that eventually we would show you that. And I believe this was the lesson we mentioned at the time, and the time is now. So let's close with this. Proves that if y equals u to the n, and n is a real number, then the derivative is n times u to the n minus 1 du. We're doing it for u, not for x, because we now have the chain rule in our toolbox. And so let's go ahead and do it. Instead of just x to the n, we can do it for u to the n. So let's start. Let's start with given y equals u to the n. Guess what I'm going to do? I'm going to take the natural log of each side. Natural log of y, natural log of u to the n. That's all I'm doing is taking the derivative of each side of the equation. Guess what I'm going to do next? I'm going to leave this alone, and I'm going to use the fact that the natural log of u to the n is n, put that exponent in front, ln of u. That's your property of logs, the power times the log rule. Now what I'm going to do is I'm going to take the derivative. The derivative of ln of y is the derivative of y, which is 1 over itself, put a y prime with it. And I'm going to take the derivative of this, and this is going to be the derivative ln of u is the derivative of u, or u prime, over itself. So that's what I get when I take this implicitly. We haven't shown every step here, okay? But that's going to be the derivative of this, which is 1 over y, put a y prime with it. It's going to be the derivative of this, which is 1 over u, put a u prime with it. Okay, what do we want? We want y prime, so let's multiply each side of the equation by y. That's all I've done here. Now, since y is u to the n, let's substitute in the place of y, u to the n. We're one step away, people. What is u to the n divided by u? Well, when you divide, you subtract exponents. This is to the first power. This is to the nth power. So if we subtract exponents, we get n minus 1. And guess what? That's exactly what we want. Look at this. Look at this. So we have proven this. So now you reach the state where not only can we say we can use the power rule for any real number exponent, we have seen that it's appropriate to do by way of proof. So we've got a lot of power here in this about now in our toolbox. Now, this was certainly no denying this. This was certainly a rather lengthy lesson. There's a lot to do, but to break it up into parts was probably not appropriate because it flows right on through. This is a type of lesson you probably will want to look at parts of it and get it down, and then move to another part and do it piecemeal till you. But basically, what was our goal? Actually, don't lose sight of the overall big picture here. A big picture, it was to get the derivative, 3 more derivative formulas in our toolbox. So our toolbox is now quite packed with derivative formulas, and probably continue to get a few more. So this completes this lecture.